upload to your Moodle, but first it will have to go through YouTube, then I'll share the link with you on Moodle. Okay, so our first topic in this course is going to be something to do with units or physical quantities, because during the rest of your physics thing, what you're going to be studying are basically different physical quantities. So we need to have an understanding, a very good understanding of what it is we're going to be doing during this course. Okay, in a physics course, you have to measure things, or you're going to do calculations with things called physical quantities. Okay, so these physical quantities have to be measured. And also, as you are aware, most of you have started doing labs. So you go into the lab, then you carry out measurements. Okay, once you carry out measurements, it doesn't end there. You have to keep a record of what it is you've measured. Then there might probably be more instructions on what you're supposed to do with your recorded measurements. Okay, the whole time you be in your lab, what you're going to be measuring and recording are things called physical quantities. You're going to measure and record different types of physical quantities during your lab sessions. Also, during the lectures and also the tutorials, we are going to talk about different physical quantities. Okay, what they mean and how do you work them out, or how do you carry out a measurement of the same. The one thing I want you to notice is that, which you're supposed to ask a question is, sorry?
Get you clear. Your network is breaking, sir.
My network is breaking how? The one thing we want you to be aware of is, for you to measure something, why would you measure something which you already know? If you already knew what something was, then what's the point of measuring it? And why are you actually trying to measure something? Okay, in my opinion, if you already knew what the length of something is, you can just tell us. There's no point in measuring something which you already know. Are we clear? Otherwise, we're just wasting our time. You go into the lab, then you spend 3 hours trying to measure things which you already know. It would be an exercise of wasting time, basically. So the point really is, this should tell you something about these physical quantities, to say, when we measure them, we carry out measurements because we do not know what the actual size or what the true value of these physical quantities is. You carry out a measurement because you want to estimate a physical quantity. You actually want to do more than that. You want to have a good estimate. You want to have a reasonable estimate of a physical quantity. And this is what we do in physics all the time. We are always estimating and trying to improve our estimation of what a physical quantity is. What we give you as the value of a physical quantity is what we think is our best estimate of this physical quantity. You never know what the true value of any physical quantity is. So you have to make peace with the fact that in physics and in many other sciences, you have to estimate. Is that clear? That's just the nature of the business we're in. You will have to estimate. Okay? And we want you to have a good estimate. Okay? So that is out of the way. So there is nothing like, oh, this is the true value of electric current, or this is the true value of this particular. No, there's nothing like that. What you have, when you go in the lab, you are all going to be estimating things. Okay? So you might be doing the same experiment. Your friend finds a different value. You find a different value. The reason why it's the case like that is because when you're measuring things, you are estimating. So there's really, most of the time, nothing wrong if the value you have found and the one which your friend has found are slightly different. Maybe unless they're completely different, then you might start asking questions. But if they are close and they're not exactly the same, there's no problem with that. Okay? You are going to carry out a measurement in order to estimate something. And you need a record of this. Okay. The other thing we're going to talk about during the course of this lecture is something called the International System of Units. Now, this International System of Units is a framework or a mechanism of measurements and weights which has been set up by scientists and engineers for use throughout the world. Okay, the first time this thing was done was in 1874, as we are going to see as our lesson progresses. Okay, so this International System of Units basically tells us how physical quantities are organized. They are organized in two groups, something called base quantities, a group called base quantities which only has got 7 physical quantities, and another group called derived quantities which has several physical quantities, most of which you know. Okay, so what are the objectives of this lesson or this lecture? By the end of this lecture, we want you to understand the following about all physical quantities which you're going to talk about in physics. In physics, we talk about physical quantities. Okay, we don't just talk about numbers like 10 or 5. No, 10, 5 doesn't mean anything in physics. In mathematics, it might mean something, but in physics, the whole of physics, when you study physics, we are talking about something called physical quantities. And there is a makeup to these physical quantities. There is going to be a number in front, so you have a number, then there's going to be a unit. For example, 10 kg. There is a 10. That 10 tells you the size of the physical quantity you're talking about. Then there is a kg. The kg is the unit of this physical quantity. So if you say 10 kg, we know that you're talking about mass, because mass is measured in kgs. If you say 10 meters or 15 meters, the 15 is telling you about the size of this particular physical quantity. Then the meter is telling you about what kind of physical quantity it is, which has got this size of 15. The meter is the unit for length. So, all physical quantities, when you're doing physics, they are presented in this combination of a number and a unit. You can't just present a number. We don't know what, if you say a number, okay, fine, that's a number. But what physical quantity is associated with this number? We don't know. So, two things. There has to be a number and there has to be a unit. All physical quantities in physics have to be presented this way. There has to be a number, 5 seconds. The 5 tells you how long something took. Then the second tells you that we are talking about time, because the second is the unit for time. Are we clear on this? I need confirmation, not just nodding your heads. Speak through the microphone.
Yes.
Are we clear on what we mean? Say, going forward, when you're talking about physical quantities, okay? Any physical quantity has got a size and it has got a unit. Okay. The other thing which we're going to talk about under the International System of Units is how these physical quantities are grouped. Okay. The first group we're going to look at is something called the SI base quantities. SI is the abbreviation for the International System of Units. So there is a group called base quantities, and we're going to look at what they are and what are their units. There is also a group called derived quantities. We're going to talk about what these are and what their units are. Now, these base quantities, there are just 7 of them. Okay, the base quantities are 7, and we're going to see what they are. Now, you are required to know by heart these 7 base quantities by the end we're done with our course. Okay. And what their units are. Then the derived quantities, these derived quantities, we obtain a derived quantity by multiplying or dividing the base quantities. So you multiply, that's how you get a product, or you get a product by multiplying, or you get a quotient by dividing. So for you to get the derived quantities, you have to multiply or you have to divide the base quantities. So you need to know some of these base quantities, derived quantities, and also their units as the course proceeds. Okay, need to admit some people. Then the other thing we're going to talk about by the time we are done with this thing is something called standard power prefixes. Now it so happens that sometimes your physical quantity is very, very large, or the physical quantity you're dealing with is very, very small. So you need to express it in a much more convenient way. And that's where these standard power prefixes come in. A prefix is something you put in front of something. So in the case of what you're trying to talk about, these prefixes, we put them in front of the unit. For example, you have the unit for length, which is the meter. Okay, that's fine. But then if you want to talk about 1,000 meters or 2,000 meters, you can say 1,000 meters, it's fine. You can write 1,000 meters, it's fine. But it's better to write 1 kilometer. Because if you say 1 kilometer, 1 km, we know that you mean 1,000 meters. And how do we know that you mean 1,000 meters? Because you put the k in front of the m. That k you've put in front of m represents a factor of 1,000. So if you say 7 kilometers, we know that you mean 7,000 meters. Sorry, 7,000 meters, yes. The k you've put in front is what we call the prefix. So there is a system of these things you put in front of units to represent something which is a physical quantity which is very, very large, or to represent a physical quantity which is very, very small. For example, when something is very small, like millimeter, the milli, okay, milli means that you get your meter rule, then you divide your meter rule into 1,000 equal parts between the 0 and the 100. You divide your meter rule into 1,000 equal parts. Each of those equal parts, that's what a milli is. So you're telling someone, in this case, when I say 10 millimeter, it means that, okay, this is 10, but then the meter has been divided into 1,000 equal parts. Okay. So basically that's what those prefixes are. So we're going to look at what they are and how to use them. Okay. So let's get started. So this international system of units, let's start with the international system of units. So the international system of units is the standard we use for measurements as scientists and engineers today. Of course, the abbreviation is SI, so you can also abbreviate it as SI. So where you see SI, we mean International System of Units. Okay. So we say SI unit for something, we mean what is the unit of this particular physical quantity in the International System of Units. Okay. The International System of Units is also referred to as the metric system, and it was established. It came into force at the International Treaty of the Meter, which was held in Paris on May 20, 1875. This treaty was signed by 17 countries. So 17 countries came together and they saw the need to have a uniform way of carrying out measurements. Okay, so that everyone, because countries had to trade and all these things, so they wanted to have a uniform way to carry out measurements, and they came up with this document, which would establish the SI system of units and also the definitions of what a kg is, what a meter is, what a second is supposed to be, and stuff like that. Every year, we celebrate this achievement, which brought into force the International System of Units on May 20. and this day is celebrated as World Metrology Day. Okay. So what did they do during this treaty? Well, they came up with a system. They came up with a system where they divided these physical quantities, or the physical quantities which were known at that time, they divided them into two groups. The first group is what is known as the base quantities, and these base quantities are 7. So they chose 7 physical quantities, and the rest of the physical quantities which were not in these 7, they became what are known as derived quantities. Derived meaning that you could obtain these physical quantities from the 7 base quantities. This table here shows you the 7 base quantities which were chosen. The first one is mass, the second one is length, then time, electric currents, temperature, amount of substance, and light intensity. So mass, the symbol for mass is small m, that's what we use in physics. Then the unit for mass is measured in kilograms. The unit name for mass is kilograms, and the symbol for the kilograms is kg, small k and a g. Then there is length. Length, the symbol is little l. Then the unit name for length is the meter, and the symbol for the meter is m. Then there's time t. Time, the symbol is small t. Then the unit name for time is second, so time is measured in seconds. Then the symbol is s. I know there are other units for these things like the hour, the minutes, and stuff like that, but we are talking about the international system of units, these physical quantities, and what are the units they are measured in. Then there is electric current. Electric current is the symbol is capital I for electric current. Then the unit name for electric current is ampere. Now ampere is different from these other units we have looked at, the kilogram, the meter, and the second, because ampere is the name of a person. So if a physical quantity, the units of a physical quantity are named after a person, then the symbol is capitalized in one form or another. So in this case, the ampere, instead of using small a, it is capital A, because ampere is the name of a person. A French scientist called André Marie Ampere lived about 300 to 400 years ago. I think in the 1700s to 1800s, that's when he lived. So which makes it 300 to 400 years ago. So if a unit is named after a person, okay, then the symbol is capitalized. Then there's temperature. Then the symbol for temperature is capital T. Then the unit name for temperature is a Kelvin. Kelvin is also the name of a person. A British scientist called Lord Kelvin, again lived in the, I think, 1700s to 1800. So the symbol for temperature is capital K. You might know temperature in your day-to-day life, and you measure your temperature in degree Celsius. That's not what we're talking about here. Under the SI system of units, the temperature, the kind of temperature we are interested in, is this one, which is measured in kelvins, and we're going to talk about these things. Next, there is something called amount of substance. The symbol for amount of substance is N, and the unit name for amount of substance is the mole, and the symbol for the mole is MOL, pronounced mole. Then there is the last one, light intensity. The symbol for light intensity is capital I. Then the name of the unit is candela. Candela is Latin. The translation, the English translation of candela is candle. Candle, like the candle, the one you switch on when there's load shedding and stuff like that. But in physics, candela or candle has got a specific meaning. Each of these units, kilogram, meter, second, ampere, Kelvin, mole, candela, they have specific meanings in physics, and we have to agree, we have to come to the same page by what we mean when you talk about mass and the kilogram, when you talk about length and the meter, when you talk about time, and the second when you talk about electric current and ampere, temperature and Kelvin, amount of substance and the mole, light intensity and candela, we have to come to the same page because we all come from different backgrounds. We have gone to different schools, but now that we are in the same class, we have to be in agreement on what it is we mean when we talk about these physical quantities. Are we clear? The definitions of these physical quantities, if you read that mass is defined in a certain way in a book 10 years ago, it might not be the same because these things they are always revised. How do we define mass? How do we define the kg? The second, there is always people who sit down and they revise these things. Okay, so this is what they came up with as the 7 base quantities of the SI system of units: mass, length, time, electric current, temperature, amount of substance, and light intensity. 7 physical quantities. I know that there are other physical quantities which you know, which are not on this list. Now, what I want to say is, if you know a physical quantity in physics which is not on this list, the first thing it tells you is that that physical quantity is not a base quantity. It's not an SI base quantity. The other thing it should tell you is that the physical quantity which you know, which is not on this list, is actually in a group which is known as SI derived quantities. Okay? And how do you get a derived quantity? You get a derived quantity by multiplying these base quantities or by dividing them or by doing both. You can do both multiplication and division. So you can do multiplication of base quantities, you get a physical quantity. You can do division of base quantities, you get a physical quantity. You can do both multiplication and division at the same time, then you get a physical quantity. So if there is a physical quantity which you know which is not on this list, then that physical quantity is an SI derived quantity. Are we clear? I need confirmation that you have understood what I'm saying.
Yes.
Okay.
Clear. Yes, exactly. Yeah, we're clear. It's excellent.
You have to know this table by heart.
Clear.
You have to know that mass is a base quantity. You also have to know the unit for mass. This table you have to know by heart. These 7 physical quantities you have to know by heart because we are going to ask you questions on these things. Okay. Apart from signing some piece of paper, which is the International Treaty of the Meter, and also putting physical quantities in groups. The first group, the 7 base quantities, then everything else in the SI derived quantities. Apart from this accomplishment, this meeting in 1875 also did something else. It established international organizations or bodies which would ensure that countries which signed this treaty abided by what was said in this treaty. Okay, some of those bodies, international bodies which were established, are what are known as there's a General Conference on Weights and Measures. There's also the International Committee on Weights and Measures, and there's something called the International Bureau of Weights and Measures. So you can go on Google, since you've got internet, to search what these bodies do. The General Conference on Weights and Measures, the International Committee of Weights and Measures, and also the International Bureau of Weights and Measures. The abbreviations look funny because these things were done in France. This meeting was done in France, so most likely the writings and everything was in French. So the thing looks funny, but just Google what the General Conference of Weights and Measures does, what the International Committee on Weights and Measures does, and what the International Bureau of Weights and Measures does. Then there are countries like Zambia, which were not there in 1875. So Zambia didn't exist in 1875 because Zambia only came into existence in 1964. So other countries which were not there in 1875 have joined this SI system of units. So once you join this SI system of units, you also have to establish organizations inside your country which are going to help ensure compliance to this treaty. And in Zambia, we have established two organizations which I think I'm aware of, do stuff which has to do with measurements and also to make sure standards are being followed. The first one is what's known as the Zambia Metrology Agency, ZMA, and the other one is the Zambia Bureau of Standards. These are the organizations which are there to ensure that things, especially the Zambia Metrology Agency, that is the organization which is there to ensure that things which have to do with measurements and weights are being followed, especially the Zambia Metrology Agency. The Zambia Bureau of Standards has to do with standards, whether standards are being followed and stuff like that. But the Zambia Metrology Agency is the organization in Zambia which is responsible to making sure that we follow the dictates, okay, and we are compliant to this the international system of units. Okay. So since 1875, when they came up with these, what the cage is supposed to be, the length, how do you define length, mass, and all these things have not been the same, because periodically these organizations, the General Conference on Weights and Measures, the International Committee on Weights and Measures, and the International Bureau of Weights and Measures, they sit down periodically, okay? After a few years, maybe 5 years or 3 years, they sit down and they discuss whether we have to change the definition of mass, or we have to change the definition of the kilogram, whether we have to change the definition of length, or whether we have to change the definition of the meter. They discuss these things, okay? So these organizations come up with what is mass? How do we define mass? How do we define length? How do we define time? How do we define temperature? When we talk about temperature, what do we mean? So that everyone is on the same page. When we talk about electric current, what do we mean? So these are the organizations which do that. They sit down periodically and they revise, they make revisions of this thing here. So let's start with mass, okay? I know we have got different ideas of what mass is, what we think the mass is, but there is a very, very specific definition of what mass is. Now, mass, nearly every object has got mass. So mass is a fundamental property, okay? And what is it? Well, mass measures something called inertia of a body. Mass is a measure of something called inertia of a body. Now, inertia in physics is defined very, very specifically. Inertia is the resistance of a body of matter to change its speed or to change its position when a force is applied. So when you're trying to apply a force, you can apply a force in two ways. You can push an object or you can pull an object, okay? Now when you push an object or when you pull an object, that object is going to offer resistance, okay? You're trying to push maybe your chair or your bed. That bed is going to offer resistance to you pushing it, okay? So the more resistance, okay, the more resistance a body offers when you apply a force because you're trying to change its position where a desk is or where a bag of charcoal is or a bag of maize is. If a bag of maize is seated in a particular position, it has been put in a particular position, then you're trying to change its position. It's going to offer resistance, okay? So the more resistance a body has, the more inertia it has. And the more inertia a particular body has, then we conclude that this body has got more mass, okay? Inertia can also be defined in terms of speed. If an object is moving, then you try to slow it down, okay, or you try to increase its speed, then it refuses. It's not going to just sit like that. If an object is moving, then you try to slow it down, it's going to offer resistance, okay? So this resistance is what you call inertia. So when you are pushing a body or when you're trying to pull a body, then this body refuses to change its position or refuses to change its velocity, then that's what inertia is. The more inertia a body has, the more mass that particular body has. And how do we know that it has got more inertia? Well, it so happens that when a body has got a lot of matter, when something has got a lot of matter, it's going to refuse to move. Okay? When something has got a lot of matter, it's going to refuse to move. That means that it has got more inertia, which means that it has got more mass. So in a way, in a nutshell, in a layman's term, you can define mass as the amount of matter in a body. Formally, mass is the measure of the inertia of a body, because the inertia depends on how much matter a body has. It's more difficult to move a body which has got more matter. For example, if there is a sack of maize which weighs 100 kg, then there's a sack of maize which weighs 20 kg or 10 kg. It's easier to move the 10 kg or the 20 kg, but it's more difficult to move the 100 kg because the 100 kg has got more matter. Are we clear? Are we clear on the definition?
Yes. We are.
You speak, don't just nod your heads without speaking.
Yes, sir.
Good. Okay. So this is what mass is. This is what mass is. For you to find out if something has got more mass or less, you need to try to move it. For example, if you've got a nail cutter or something like that, you need to try to move something. If it's easy to move, then it tells you this object has got. If you have got a nail cutter, then you move it around. You can't tell us that nail cutter weighs 100 kg, has got a mass of 100 kg. It doesn't work like that. Okay? If something is easy to move, it means that the mass is less. So it needs to have a small size of mass. So you can tell us maybe it has got 10 grams or whatever it is, maybe 100 grams. Okay? But if something is difficult to move, then that tells you this thing has got more mass. So how do you find out that something has got mass? You try to move it. You try to push it or you try to pull it. If someone is running, your friend is running, then you pull them easily. They don't have a lot of mass. But if your friend is running, then you try to pull them, then you're having difficulty, they pull you along, then that person has got a lot of mass. Okay. Mass is measured. Yes? There's a question?
Yes, sir.
Yes.
Well, what does it mean when we say mass is a fundamental property?
Because every object has got mass. It's there. Every object has got mass. Okay, now Harry. This is very interesting. Someone is sleeping. Are you sleeping? If you are asleep, Harry. Yo. All right. Okay. So mass is measured in kilograms. Okay, and the abbreviation for the kilogram is kg. Okay. Now from 1875, the kg has been defined in terms of objects. So there is this object which these guys, this meeting thing, when they sit and discuss what they decided to say the kg is going to be based on this particular object. So there is this object in this diagram here, that cylinder inside this thing. This cylinder is kept at the International Bureau of Weights and Measures in France. That cylinder, the first time they decided to make the kg, the cylinder was made up of platinum only. Okay, so the cylinder was made of platinum. But then they decided later on, as the years went by, they decided to change to make the cylinder out of platinum and iridium. So basically, it used to be made up of platinum and iridium. And the reason why they did this, trying to make the kg out of platinum and iridium, is because this alloy of platinum and iridium could not easily corrode. So you could be sure that the same amount of matter you had in 1875 is the same amount of matter you have now, because platinum and iridium, this alloy, does not corrode very easily. Okay, so the kg used to be defined in terms of this metallic cylinder, and the countries which attended the first treaty, the International Treaty of the Meter, they were given copies of this cylinder, and those copies of the cylinder which they were given, they became their national copies, what are called in national prototype kilogram. So the one which is in France, which was kept in France, is the one which was called the International Prototype Kilogram. So what I want you to understand is that after 1875, and for a very long time, from 1875 to 2019, the kg used to be defined in terms of an object or an artifact. Okay. However, after 2009, the kg, the definition of the kg changed. Okay, it was now defined in terms of something called Planck's constant. Planck's constant is a physical constant, like the way you have the speed of light. So Planck's constant is a physical constant of physics, and in your chemistry classes, I think you're going to talk more about what Planck's constant is. So at the meeting which was held in 2019, which is like 3 years ago, at the International Metric Convention, the kilogram was officially redefined in terms of this Planck's constant. So the definition of what a kilogram is these days, since 3 years ago, is no longer in terms of an object, okay, but it is in terms of this constant, Planck's constant. And you can see what the value of Planck's constant is: 6.6207015 times 10 to the power minus 3 joules per second, or the equivalent is this, which is kgs meter squared per second. Okay, so that's what Planck's constant is. So now, these days, the definition of the kilogram is in terms of Planck's constant. But even as we define things in terms of other things, the amount of matter has to be the same. It has to remain the same. So it doesn't mean that we now have less matter or we have got more matter, but the amount of matter when you redefine something still needs to be the same. Are we clear? You as a medical class, what is important is that you understand to say mass, what mass is. Mass refers to a measurement of inertia or an amount of matter, and that mass is measured in kilograms. Previously, the kilogram was defined in terms of an object. That is no longer the case. Even as we have changed the definition of the kilogram, what has changed, what has not changed, is how much matter is there. There is no increase in the amount of matter or decrease in the amount of matter, even as we have changed the definition of the kilogram from an object into a physical constant. Okay, are we clear? We are not going to ask you to define what a kg is. No. We want you to know that mass is measured in kgs, and that a kg is now defined in terms of a physical constant called Planck's constant. Then we move on to length. Length is also defined in a very specific manner. Okay, the length refers to a straight line distance between 2 points. This is how we define length: the straight line distance between 2 points along an object. So if the distance is not straight, we're talking about something else. So that's what you mean by length: straight line distance between 2 points along an object. Okay, that's a definition. And the SI units for length is the meter, and the symbol for the meter is m. Again, for a very long time, from 1875 up to last year, many physical quantities were defined in terms of objects. In the case of length, length used to be defined in terms of a bar, a metal bar, a flat metal bar. Okay, that flat metal bar was made of platinum, but as some of you might be aware who have held bars, for example, a 1 meter bar, a metal bar, or a plastic meter roller, you will notice that metals tend to bend. So after some time, after realizing the problem of bending and stuff like that, these guys decided to change. Okay, say, okay, fine. Instead of using a flat bar, we're going to use an X-shaped bar. An X-shaped bar does not easily change, does not easily bend. And also, they changed the material from just platinum to an alloy of platinum and iridium. So you, again, were assured that this bar would not corrode. The other thing about this bar, which used to be the meter, because this bar is no longer the meter. This bar used to be called the standard meter for a long time, from 1875 up to 2019. This kind of bar was what is referred to as the meter. So it's an object. It used to be a meter, used to be defined in terms of an object, the same way the kg used to be defined in terms of an object. This bar, like your meter ruler, was longer than the meter, so it had markings. Say this, between this marking and this marking, that's what the meter is, so that if it got damaged in any way, you could still use it to define what the meter was. Okay. So again, the meter was defined in terms of an object, which is that X-shaped bar. However, that is no longer the case. From 2019 again, the meter is now defined in terms of the speed of light. Okay, and how is that? Well, the speed of light in vacuum is a constant. The speed of light in vacuum is a constant, which is approximately 3 times 10 to the power 8 meters per second. That 3 times 10 to the power 8 meters per second is 300 million meters per second. So we say light travels a distance of 300 million meters in 1 second. Okay? So the meter is defined as follows in terms of the speed of light. 1 meter is defined as the distance light travels in vacuum during a time interval of 1 over 299,792,458 of a second. So this is how we define the meter. It's like you get this distance light travels in 1 second, then you divide it into equal parts, which are equal to that many things. So you divide it into equal parts. So 1 over this, in 1 over 299,792,458 of a second, light is going to travel a distance of 1 meter. Are we clear?
No. Yes, we are.
Someone said no. No. What's the problem? The one who said no. Where are you not clear?
On the part where you explain the constant for speed of light.
You know what the speed of light is? Hello?
Yes.
What is it?
300 million meters per second.
Yes. So basically that means that light travels a distance of 300 million meters per second. So imagine this distance traveled by light, okay? Then the distance traveled by light, you chop it into 300 million equal parts. The distance which light travels, then you cut it into 300 million equal parts. What do you think you're going to get? How much is going to be each part? One what?
So meter.
Yes, you're going to get 1 meter. So the distance which light travels in 1 second, which is 300 million meters in 1 second, if you get that distance, then you chop that distance into 300 equal parts. You get the distance and then divide it into 300 equal parts. You're going to get 1 meter. Now, light For light to cover that 1 meter, the amount of time it needs is this: 1 over 299,792,458 of a second. Because in 1 second it covers 300 million. So for it to cover the 1 meter, it needs this amount of time: 1 over 299,792,458 of a second. Are you clear?
Yes, I am.
Okay. So we have to come to an end here unless there are any questions. So the recording of this video is being made. We're going to upload it to YouTube, and also we're going to upload it to your Moodle. So there's going to be a link in your Moodle taking you to the YouTube video so that you can watch at any time what you have discussed during the course of the year. If you want to go back to this material, you're also going to have the notes, but maybe if you want to listen to the explanations of what we are talking about, then you know where to go. Are we clear? So unless people have got questions, the labs are ongoing. There are labs happening. So you need to find yourself a tutorial group, and you need to know on which particular day your labs are happening. I don't deal with the labs so much, but yeah, they are colliding with lectures. Okay, so yeah, so I don't know what we're going to do about that. The issue with the labs is you only have to do your labs for the next 4 weeks. So I don't know if your lab is colliding with a lecture. You have to go and talk to the head of department or the assistant registrar so that they can sort out this thing of collision. Any other question? Okay, so if that all right, then we can come to an end here. We are going to meet, we're going to discuss further. I think we have a class on Monday or something like that next week. So this is just the start. Okay, then yeah, then see you then. So we have to come to an end here. Someone is saying the books. What other books do you suggest we read? Well, to start with, as much as you are doing physics for medical sciences, it is still a physics course. Okay? It is still a physics course. So which means any physics book is good. We have a book called Principles of Physics. There are some books you can go to the bookshop, you buy college physics or Shom's, whatever it is. As long as it's a physics book, it is still a good book. So this is still a physics course. Then there are also books you have posted on Moodle. The books you have posted on Moodle, show that show some medical applications. Okay, so someone says we are meeting on Monday, 14 hours. So that's when you're supposed to meet. That's what's on Moodle, and that's exactly the way it is. So you know when you're supposed to meet and when you're supposed to log on and stuff like that. Okay. Who is the moderator for the tutorials? The tutorials haven't yet started. Okay. The tutorials, your physical tutorials have not yet started. However, you are going to be assigned a tutor for your tutorials, and at the same time, I also perform an online tutorial. But this online tutorial will be between 20 hours and 21 hours. So you're going to choose days, because I teach your course, your PHY 1015. I also teach PHY 1010. So I'm going to choose 2 days for your PHY 1015, another 2 days for PHY 1010. So that you can be discussing problems, so that you learn how to solve problems, because attending lectures and listening to lectures as I'm talking is not enough in a physics class. You need to learn how to solve problems. So during these tutorial sessions, which in my case I'm going to put at night from 20 hours to 21 hours, during those hours throughout the year, you will learn how to discuss, how to solve problems through a discussion. Okay, I'll ask questions, then you participate. That way, hopefully, you will see how you go about solving problems in physics. It doesn't have to do with memory. Once you understand something in physics, you don't need your memory. You just need to understand the steps you take to solve a problem. Okay, so again, in the next couple of weeks, we're going to post the links for that. We have to come to an end here. So unless people have got questions, we need to end. I'll post the video recording on YouTube and also on Moodle. Okay, so I'll see you on Monday.